This unit, we're going to be looking at what is known as integral calculus, the general idea of which, in layman's terms, is to calculate the area between the curve of a certain function and the x-axis, and how we can connect that to differential calculus, aka derivatives. So we'll start by taking a look at how we can approximate the area, and from here, based off of this idea of approximating areas, how we can get an exact idea of what the area is between a curve of a function and its x-axis. So, area function regions, okay? So in terms of mathematical notation, the area between a curve of a function f and the x-axis over some interval a to b is what we call a definite integral, okay? So this area is known as a definite integral, and it's represented by the following notation. Area equals the definite integral from x equals a to x equals b of f of x times d of x, okay? Let's take a look at what all this notation means right here. So this fancy looking s right here is what we call the integral sign. I'm sure there's a more fancy name for it, a more formal name for it, but I do not know what that name is. Okay. A is called the lower bound, while b is the upper bound of integration. The bounds represent the interval in which we are interested in finding the area between the curve and the x-axis. The function f of x in the integral is what we call the integrand. Okay, so f right here is going to be our integrand. And then dx represents a very small change in x, and we call it a differential, just as we saw with derivatives. We can think of dx, dz, or d whatever as a very small change in whatever that quantity may be. Okay? So how do we go about approximating the area between a curve and the x-axis? So what we can do here is we can break up a curve into rectangles, what we call Riemann sums, named after a mathematician who first formulated the concept, Bernard Riemann. So we can break it up into rectangles right here that roughly approximate the area between the curve and the x-axis. Okay? Please take a note that for each rectangle, the area is going to be the interval of change, delta x, okay, times our height, which is going to be f of x, all right? The height at that certain specific x value for our rectangle, okay? So we're going to have our height, f of x, times our width, delta x, our change in x, which is going to give us the area of one single rectangle, what we'll call a of k, where k represents the kth rectangle. So this would be the fifth rectangle, k would equal 5 here, k would equal 4, 3, 2, 1, so on and so forth. So that's going to be equal to f of x sub k times delta x. All right, so now how do we go about calculating delta x? So delta x, what we're going to do is if we think of this right here, this x value is a and this x value is b, delta x is essentially going to be the equal subdivisions of this interval ab. So what we're going to do is we're going to take the size of our interval ab, which is going to be b minus a. All right, so that's our size of the interval, and we're going to divide it by the number of rectangles n that we are using to approximate our area. So delta x will equal b minus a divided by n. All right, so now we're going to take a look at how we can calculate out what x of k is, x sub k is, aka x1, x2, x3, x4, x5, so on and so forth, okay? So if this is a right here, x1 is going to be equal to a plus delta x, okay? Now if we want to get to x2, which is located right here, we have to move two delta x's over from a. So x2 is going to be equal to a plus delta x equals a plus 2 delta x. Now same thing if we want to move to x3 right here, okay, from x equals a, we're going to have to move over 3 delta x's. So we're going to have x of sub 3 equals a plus delta x plus delta x plus delta x equals a plus 3 delta x. So in general, we can say is that for x sub k, where x sub k is our kth x value, that's going to be equal to a, our initial x value, plus k times delta x, where k is, again, our interval that we're interested in. So as a result, we're going to get that if we substitute x sub k in right here into our equation for the area of a single rectangle, we're going to get that a of k equals f of a plus k delta x. Again, we substitute that in for x sub k times delta x. Okay, so this right here is the function value evaluated at a plus k delta x, or x sub k value. All this may seem a little bit esoteric. When practiced, it's not too bad. Okay, so we write that the Riemann sum then. We write that our definite integral from a to b of f of x d of x is approximately equal to the sum of all the rectangles that we have that we're using to approximate our area. The sum of the n rectangles that we're using to approximate our area. All right, so sigma k equals 1 up until n, where n is the number of rectangles we have, of each individual area of each rectangle. Okay, if we substitute in the equation for a of k that we got on the prior slide, we're going to get that sigma k equals 1 up until n, f of a plus k delta x times delta x is approximately equal to our definite integral. So our definite integral is approximately equal to some of these area of rectangles that we find under each individual interval, or better said, subinterval. So one important thing to note, since f of x can be negative, the area can be negative as well. All right, so this area right here, this blue region, all right, these blue regions right here would have positive areas, okay, corresponding to positive heights, positive function values, whereas this yellow region right here, this gold region, would have a negative area since the height is going to be negative over this specific interval. So the left endpoint approximation and error, all right? So there are two different ways that we can take rectangular approximations, two main different ways, excuse me, for right now. We can use a left endpoint or we can use a right endpoint for our heights. So what does the left endpoint look like? So the left endpoint, okay, means that we're going to use the left endpoint of each subinterval. So A for its first rectangle, x sub 1 as our second rectangle, so on and so forth. And we're going to use that as the x value to evaluate our function and to determine the height of our function over that specific interval. So f of A is a height right here. For his first rectangle, f of x1 is the height for his second rectangle, f of x2 is the height for his third rectangle, so on and so forth. Note that, all right, because B is the rightmost endpoint, f of b is not going to be used as the height of a rectangle because it is the rightmost endpoint, whereas we're using the leftmost endpoints right here. Okay? So procedure follows. We're first going to determine delta x. Remember, delta x is going to be b minus a divided by n. And then in a table, we're going to determine our left endpoint, starting at x equals a and incrementing by delta x. And then in the same table, we're going to calculate the corresponding values of f at each left endpoint. Okay? So in the same table, we're going to calculate the corresponding values of f at each left endpoint. And then lastly, we'll calculate the area of each subinterval and add together the areas. Okay? So it's nothing more than a little bit of multiplication and addition in practice, even though it may seem very abstract and esoteric in theory. So now when it comes to errors, because there are errors associated with these approximations, okay? If we take a look at the two graphs that we have right here, we see that if a function f is decreasing, we see that our function, our approximation is going to exceed the actual value of the area between the curve and the f-axis. Whereas if our function is now increasing, the left endpoint approximation is going to be less than the actual area between the curve and the x-axis. So taking into account that we're going to be decreasing when our derivative over a certain interval is less than 0, and we're going to be increasing when our derivative over a certain interval is greater than 0, we can come to the following conditions. If f prime of delta x is less than 0 over an interval, then the left endpoint approximation will be greater than the actual area value of the area. And then if f prime of x is greater than 0 over an interval, meaning f is increasing over that interval, then the left endpoint approximation will be less than the actual value of the area. So now let's move on to right endpoint approximation and error. So right endpoint approximation is very similar and uses the exact same steps as the left endpoint approximation, except now you're not going to use f of a, okay, because a is the leftmost endpoint, but instead we're going to use the rightmost endpoint of each subinterval. So instead of starting at x equals a, we're going to start at x1, and then we're going to proceed to x2, x3, and up to b. And then we're going to use these right endpoints, x1, x2, and x3, and b, to evaluate the height of each individual rectangle, aka f of x1, f of x2, f of x3, and f of b. Okay, so f of a will not be used in the right endpoint approximation. We're going to start the table at a plus delta x, which is going to give us our x1, and we're going to increment until we reach the value of b at the endpoint of our interval. In terms of error approximations, okay? Email popped back up here. So, in terms of error approximations, okay? And let's check and see, make sure email doesn't do that again. Sometimes it does it. Very weird. I've never figured that out. All right. Anyway, so if we take a look at our graph right here, we see that if f is a decreasing function over an interval, meaning our derivative of f is less than 0 over that interval, we see at the right endpoint approximation yields an area that is less than the actual area between the curve and the x-axis. Whereas if our function is increasing, meaning our derivative is greater than 0 over a specific interval, we see that our function is going to be greater than 0, or excuse me, we can see that our right endpoint approximation is going to be greater than and exceed the actual value of the curve area between the curve and the x-axis. So we have the following conditions: that if our derivative is less than 0 over an interval, then the right endpoint approximation will be less than the actual value of the area. Whereas if our derivative is greater than 0 over an interval, okay, then the right endpoint approximation will be greater than the actual value of the area. So approximation summary is that if we use the left endpoint and our function is decreasing over interval, the area will be greater than the approximation will be greater than the actual area. Whereas if it's increasing, all right, over an interval, the left endpoint area will be less than the actual area, okay? And then this reverses if we do the right endpoint. So if we're decreasing for right endpoint, it will be less than the actual area. The approximation will be less than the actual area, and if we're increasing over an interval, the right endpoint approximation will be greater than the actual area. So let's take a look here, all right, at this example right here, okay? Evaluate the integral from x equals 1 to x equals 5 of x cubed dx using a left Riemann sum of 4 subintervals of equal width. Determine if the approximation is less than or greater than the actual value of the integral. So we follow our steps right here. First we determine delta x, which is going to be from our a is right here is 1, our b is 5. So our delta x is going to be 5 minus 1, b minus a, divided by 4, which gives us a delta x of 1. So if we're using a left endpoint sum, that means we're going to start x equals 1, and we're going to increment by delta x. So we're going to start at 1, increment by 1 to get 2, 3, 4, and 5. For a left endpoint, please note we're not going to need 5 here, but I'm writing it down in the case that we need it for the right endpoint, which we'll see in a second, okay? So now when we evaluate our integral, we have to evaluate the areas of each specific subinterval. So that means we're going to have f of 1 times delta x. We're going to have f of 2 times delta x. We're going to have f of 3 times delta x. And then we're going to have f of 4 times delta x. Okay? So f of 1 is just 1, f of 2 is 8, f of 3 is 27, and f of 4 is 64. So we're going to have 1 times 1, 8 times 1, 27 times 1, and 64 times 1, which altogether gives us an approximate area of 100 for our integral here. So now let's take a look at what the error looks like. So for the error, we need to know if our function is decreasing or not, or decreasing or increasing over a specific interval. So we have to use the first derivative test. Okay? So for the error, we use the first derivative test. Our first derivative of x cubed is going to be 3x squared, which means we're going to have a critical point at x equals 0. Okay? So if we go ahead and evaluate the derivative of f of 3x squared to the left and to the right of x equals 0, we can see that our derivative is going to be positive right here. For x less than 0, our derivative will be positive for x greater than 0. So since our derivative is always going to be greater than 0, and a left Riemann sum is going to be used, that means that we're going to have an under approximation, meaning that our approximation we calculated 100 right here is going to be less than the actual value of this integral. So now we look at a similar scenario where now we use a right Riemann sum of 4 subintervals of equal width. Determine the approximation is less than or greater than the actual value of the actual value of the integral. So we can skip to step 4 because we already calculated delta x and we already calculated our table, except now we're not going to start at the leftmost endpoint, but we're going to start at x equals 2. Again, we start at the point next to our leftmost endpoint, and then we start incrementing. So we're going to start x equals 2, and now we use x equals 5. So we're going to have f of 2 times delta x plus f of 3 times delta x plus f of 4 times delta x plus f of 5 delta x to give us the area of each individual rectangle. So that's going to give us a times 8 times 1, 27 times 1, and 64 times 1, plus 125 times 1, which is approximately equal to 224. So now in terms of valuing the error, we saw that in our last example, okay, that this function is going to be increasing, meaning the derivative will always be greater than 0 for this specific interval. So as a result, 224 is going to be greater than our actual value of our integral, meaning we have an over-approximation here. All right? So as a result, we know that our integral must be between 100, what we calculated using the left Riemann sum, and 224, what we calculated using the right Riemann sum. And these are the introduction, and this is the introduction for approximating areas between curves.